At this point, we have seen that the critical section problem can be solved in several different ways. We are going to look into one more solution, which has some extra nice property, the Lamport's bakery algorithm. Lamport is one of the recipients of the Turing Award and came up with the following idea. Simply put, all the threads who want to enter a critical section need to get a number. The thread with the smallest number is the one that can enter. Imagine a take-a-number system, basically. We assume the numbers given by the take-a-number system are non-decreasing. Non-decreasing means that two or more consecutive numbers can be the same. If we also assume each thread has a unique ID, we can break ties, saying that if two or more threads have the same number, the one with the smallest ID can enter its critical section. Let's look at the complete example. We have two shared arrays, each with n elements. N is the number of threads. The first array, choosing, contains booleans initialized to false. The second array, number, contains integers initialized to 0. In its entry section, thread I starts by setting true to its entry in choosing. Then it computes the max value for all entries in number plus 1 and stores it in its number entry. Finally, it sets false to its entry in choosing. Then it does a complete pass over the n entries of the array, but it spins on each entry j if such an entry is choosing, or if such an entry has a lower number j combination, but the number is not 0. Number j combination because we use threads ID to break ties. Then it enters the section. Once the critical section is over, the thread simply sets its number back to 0. Before discussing why this solution is valid, please notice that each thread is only modifying its own entry in the array. I ask you to formally reason about why this solution is valid. I'm only doing a rapid discussion. For mutual exclusion, you can conclude that if a thread enters its critical section, then the thread is sure no other thread has a lower number. When the thread is in, can another thread obtain a lower number and enter the critical section? No, because the number is always the max of all threads plus 1. So it will be at least plus 1 compared to the thread that is running its critical section. When it comes to progress, the thread with the smallest number can always proceed. When it comes to fairness, notice that once a thread starts waiting and another enters its critical section, the next number the latter will get is higher than that of the waiting thread. Now, going back to what I said in the beginning about the nice property of this algorithm, is that it works also with primitives that are weaker than atomic read-write. In fact, this is one of the algorithms that gave rise to research in lock-free synchronization.